We are now in week 5. You guys are doing amazing, so keep it up. This week on Monday, we don't have a quiz. So you'll see that we sort of started strong, kind of set the tone. And then we were getting too backed up with the material. You wouldn't be ready to take a quiz tonight on work on Module 5. So we're taking a week break before you take the quiz on 4B and 5. So if you look at that whole day by day for the whole semester, you'll see that the quizzes kind of come in these smaller chunks with a little bit of break in between so you can catch your breath. There's still video notes and new content as we're going through that, but hopefully it helps make it a little bit more manageable. Okay, so for this past week's content that I answered a lot of questions on, and I feel like I want to reinforce, I'm going to first go back to Module 4B. I think the hardest part about that for most people was ramps versus friction or circles. So for ramps, with Newton's second law, just remember, for Newton's second law, we always want to follow the steps, right? No matter what we're doing with it, there's 3 steps: diagram, sum of individual forces, plus MA, minus MA, or 0, on repeat, over and over and over and over. And if you get used to the steps, it will always work. So let's say we're going to do a block sliding down a ramp with friction. So let's say that I have here a block, and it's going to be having some friction on the surface, but let's say that it's overcome that friction and that it is, in fact, sliding down the ramp. Okay, so that's the setup of our problem, and we'll give the ramp some angle m, some angle theta, and the mass of the block some m. So step 1. I'm going to draw a free body diagram, right? We love our free body diagrams. I draw mine tilted because I'm on a ramp. And so we are going to have a couple forces. We have mg, the weight, always towards the center of the to the center of the earth. And then we're going to have, in this case, the normal force, which is a perpendicular contact force, right? That's what normal force means, perpendicular contact force. So it's perpendicular to the surface. And then because we have friction that opposes motion. It's always parallel to the surface, and it always opposes the direction of motion. It's sliding, so that's my kinetic friction. I sometimes at this point already put mu sub k times n, just to remind myself of that formula, skip the middleman of writing F sub k. I'm not done with my free body diagram. I need 2 more things. I need to draw my axes, and on a ramp, we tilt our axes, X and Y. I'm going to be stubborn and take my positive right-handed coordinate system. So in this case, X is up the ramp. Again, you'll see it doesn't matter as long as I'm consistent. And then my acceleration, near but not on the diagram, with a double arrow. So this is my step 1. A good free body diagram is pretty much more than half the battle. So now let's go ahead on to step 2. Here we have to do X and Y separate, right? So we have to do X and Y separate. And so if I look at the sum of forces in the X direction, then I'm going to see here that I have 2 forces in X. I have friction, right, which points, according to me, in the positive X direction. So I'm going to write positive mu sub k n. And then I also have the component of friction in the parallel direction. We know, and you can review the video notes as needed for this, right? But here's my triangle. MG is the hypotenuse of this right triangle because I want to get the components of MG. So I think the way to draw it at this point would be to make sure that you know that MG is my hypotenuse. And so now I'm just trying to draw out those components. We saw from the video that angle is also theta, the angle of the ramp, which makes this component here mg sine theta. So we end up here With this, it's pointed down the ramp in my negative x direction, right? Negative x compared to what I've called positive up the ramp. So I write minus mg sine theta. That's my step 2 for the x direction. I'm going to move on to step 3. So equals plus ma minus ma or 0. We see that acceleration is in my negative x direction. So I write minus ma. This was step 3. And so I then end up over here with this equation of motion for x. So that's my x equation. And so I press pause because I'm not done. I have my y equation. So now I need to go ahead and let's do what this would look like in y. So the sum of forces in y, I'm going to look and I'm going to have here my normal force in my positive y direction. So I write plus n, and then I have this component of the weight that's down into the ramp, that's in my negative y direction, so minus, and it's the adjacent side of that triangle, so minus mg cosine theta. I'm not accelerating off the ramp, so that equals 0. I give that a nice box, and this is, oops, meant to make that red to keep it pretty, but that's my y equation. And so at this point now I get to just solve things. So let's say I want the acceleration first here because I have friction. I need my normal force, as you hopefully know by now, n equals mg cosine theta on a ramp. I go ahead and I plug that in for my normal force there. And so then that x equation would become mu sub k mg cosine theta minus mg sine theta equals negative ma. I can divide the whole thing by negative m and I'd have my acceleration and I'd be all set. Okay, so that's a review of the steps, right? And I did it for ramps because I felt like that was the trickiest thing for a nice review, but added in some friction, draw our diagram, axes and acceleration, stick to it. And then sum of forces in each direction, sum the individual forces, and then decide if it equals plus ma, minus ma, or 0, based on how your acceleration arrow lines up with your axes. Okay, so that was 4B. For 5 on work, I think the most useful thing that I can point you to is this page. This was page 20 of the course packet. So page 20 of your course packet. First of all, the course packet is super useful because if you're stuck on things, there's problems here that you can then work out. You have explanations for each step. And if you get stuck, you can ask me very specific questions. And some of you are doing that. And I feel like it's working really effectively to learn the problem solving steps because I have full worked examples with annotations. You work that problem step by step and make sure you understand every single step. Ask questions when you get stuck, and then you can apply that problem, those steps to your unfamiliar problems. So page 20, that's what this is here. So this is page 20. This has everything you need for all the Module 5 problems in one page, literally. So if you know how to use this page, you're set. One thing I'm seeing is that people are sometimes integrating when you have a constant force. It's not wrong, it's just harder. So if you have a constant force, it could be in 1D or 2D. So for example, you might be given a force like in the daily check where the force is equal to say 3I hat minus 4 j hat, I'm just making that up. And let's say that there's some displacement that's equal to 2I hat plus, I don't know, let's say 3 j hat meters. So in this case, this is a constant force. It's like, feels like a function because it has the I hat and j hat and maybe feels a little unfamiliar, but it's not changing. It's not changing with position. It's not changing with time. It's just constant. So you can use this. Then you would use this component method of finding the force. F sub x is 3, delta x is 2, And then my I hats and j hats go away. Dot product, not a vector anymore. F sub y is -4 and delta y is 3. And then I don't have z components, so 0 and 0. And so I end up with 6 minus 12, and that would be -6 joules. -6 joules of work, no big deal. It can be negative. That just means that I lost kinetic energy. I slowed down. So that's what that means. So don't be fooled that you have a non-constant force just because it's 2 or 3 dimensional. There's an easy shortcut for that. If you have a force and it is a function, something like f of x equals, ax to the 5th, for example, right? Then you would use the integral. Or if you have multiple dimensions where you have f of x and y, then you use this longer version, sort of worst case scenario, I like to say, where you plug into that equation down there. So this page, again, page 20 of the course packet is your best friend for Module 5. It's different than my other annotated examples because with work, it's more about find the equation, use the equation. And then remembering that work relates to speed through our work kinetic energy theorem. All right, everybody, you are doing amazing. So we will continue going through module 6 and 7 this week, but then we're going to have some, kind of time where you'll come back, kind of take your quiz on 4B and 5. That'll give you plenty of time to ask questions before you take your quiz on the topics. And then over the July 4th weekend, I kind of have a nice mini break scheduled for us, like we might get in the middle of a semester, because 12 weeks is a long time. And so keep up the hard work. I am really impressed. And for those of you that are like really active on Discord, either through DMing me or on that main channel, great job. That's really, the best resource that I have for this asynchronous course. So, all right, guys, nice job.